Hi, this is Chuck. Welcome to this video where we are going to continue looking at mechanical vibrations. In this case, we're going to look at critical, under, and overdamped systems. When we look at these, we are still not going to be applying an external force. So our equation, our displacement equation, is going to look like mu double prime plus gamma u prime plus ku equals 0. The right-hand side is still 0. As I mentioned, no external forces are being applied. This will give us a second-order linear homogeneous equation, which I'm assuming you know how to solve. These are usually pretty straightforward. First thing we're going to do is we're going to convert this to the characteristic equation, mr squared plus gamma r plus k equals 0. And if you'll recall, using the quadratic formula, which is going to be a minus gamma plus or minus the square root of gamma squared minus 4mk over 2m. And this is going to give us our solutions for our roots. They could be root 1 and root 2 or whatever it is. Okay, there are three possible outcomes here. The first of these is that the gamma squared minus 4mk equals 0. In other words, the discriminant, the stuff inside of this square root, is 0. And it gives us then negative gamma plus or minus 0 over 2m, or just negative gamma over 2m, as our root. When we have a double root, recall that when we're creating our solution, the displacement equation, one term is just going to be e with the exponent. The other term is going to be our independent variable, in this case t times e to the same exponent. One of the things to notice here is if we let t go to infinity for our displacement equation, it's going to go to 0. And recall that it's going to go to 0 because as t gets larger, this exponent is going to become larger negative valued. This will also become a larger negative value, which is going to force that e to the whatever that exponent is to 0. And of course, anything times 0 is 0. This is what we really want to have. Okay, let's keep it fairly simple, something that you're familiar with. Let's talk about the suspension on your car. What this says is that over time, the displacement, the movement up and down, is going to go to 0, which is exactly what you want. Your suspension has McPherson struts or shock absorbers, one or the other on it. It has some other stuff too, but we'll limit our conversation to that. Are going to stop that tire from bouncing up and down after you hit a bump. So if you hit a pothole or a speed bump or whatever the case might be, the tire is going to move from its natural position. It's going to deflect upward, come back down. You don't want that tire to be going up and down and up and down and up and down. Okay? In this case, you don't see, well, we're going to see a little bit later when you graph these, that in some cases you don't have any oscillation. This does not have any oscillation to it. The tire deflects from its natural position, goes back to its natural position. That is referred to as being critically damped. When a system is critically damped, we have our gamma squared minus our 4mk equals 0. We can solve here for gamma by moving the 4mk to the right-hand side and taking the square root. And what we're going to wind up with is a value for our damping system where we are critically damped. Okay, and that's going to be our gamma is equal to 2 times the square root of m times k. A second scenario that can play out is that the discriminant is positive. This means that the m squared minus the 4mk, I have a plus here for some reason, minus the 4mk is greater than 0. This will give us two roots. Okay. Now, recall that these roots here are going to just be the quadratic formula. So it's going to be negative of gamma plus or minus the square root of gamma squared minus 4mk over 2m. If we do a little bit of algebra here in the next step down, What we can do here is inside of the square root, we can factor out a gamma squared. When we factor out the gamma squared from this first term, it's going to leave us with a 1. Now, to factor gamma squared out of the 4mk, it's going to leave us with 4mk over gamma squared. Nevertheless, we have factored gamma out of that discriminant. When we take and then factor out from both terms in the numerator, we can factor out gamma. And in fact, I'm going to factor out the negative of gamma. And then from the denominator, I'm going to factor out the 2m. What we are left with is the negative of gamma over 2m times 1 plus or minus the square root of 1 minus 4mk over gamma squared. Okay, so what does this give us? When we factor out the negative gamma over 2m, we have this 1 plus or minus the square root. And what we need to do is consider what's the value of that going to be, the numeric value. Well, we're going to have that 1 is greater than the 4mk over gamma squared. I'm looking at the two terms inside the square root. So this is going to give us then that this 1 minus 4mk is going to be somewhere between 0 and 1. How do I know this? Well, if you'll recall, up here, we have a relationship between the 4mk and the gamma squared. If it's critically damped, they're equal. In this case here, what's going to wind up happening is we're going to have the gamma squared minus the 4mk greater than 0, which is what we're assuming. Okay, recall up at the top left corner here. And if we assume that it's greater than 0, this gives us that the gamma squared is going to be greater than the 4mk. So if the gamma squared is greater than the 4mk, that means that this fraction right there has to be smaller than 1. And 1 minus something smaller than 1, as in between 0 and 1, is going to give us a value between 0 and 1. All right, this then allows us to determine that the square root of this 1 minus the 4mk over gamma squared is going to be less than 1 because the value inside cannot be any larger than 1. In fact, it's going to be smaller than 1. Okay. When we work with that then, we know that 1 plus or minus, so what I'm doing is I'm moving further out in my equation. Okay, I'm now looking at this whole thing right here, the 1 plus or minus the square root. And remember, we just determined that the square root itself is less than 1. So if we do the 1 plus or minus the square root, this is going to have to be larger than 0. If it's the plus, it could be as big as 2, as small as 1. If it's the negative, so we have 1 minus the square root, this could be anywhere from 0 to 1. So the value on this, if you do the plus minus, is somewhere between 0 and 2, which is, notice I said between, not including 0. So this is going to be somewhere between 0 and 2. It's going to be greater than 0. Now, if I go back up to that equation where I just was, equation 1, I have the negative gamma over 2m plus or minus 1, times 1 plus or minus this 1 minus the 4mk over gamma squared. Okay. I know that this is going to be a negative. Well, how do I know that? Well, gamma is positive. I'm looking here at the first portion, the first factor. The gamma itself is positive. 2 times m, m's the mass, it's going to be a positive mass. So gamma over 2m is a positive value. With it having a negative multiplied times gamma, that first fraction's always going to be negative. As we just discussed, the 1 plus or minus the square root is always going to be positive. This gives us then a factor that's negative times a factor that's positive this product will always be negative. So this tells us that our two roots, R1 and R2, are both going to be negative values. So what we're going to have here is C e to the R1t plus C e to the R2t. And remember, R1 and R2 are both negative, so those exponents are both negative. When we apply the limit as t goes to infinity on our displacement equation, once again, just like we saw before, this is going to go to 0 over time. Okay. The mass winds up being restored to its original position. Okay, as in case 1 above, the mass is restored. In this case, though, we're going to have r squared is greater than 4 times mk, where r is greater than 2 times the square root of mk, which means that our damping constant now is going to be larger than the critical damping constant. Okay. If our damping constant, which we will have in this case, is greater than the critical damping, this is said to be overdamped. Okay, so how does that feel in a car? Well, what this essentially is going to give you is a ride where you have the car hitting a bump, and man, do you feel it. It's like riding in an empty truck where it goes boom. Okay, it gives a hard ride where you feel more of the bump. Once again, the tire doesn't continue to oscillate back and forth. In fact, it may feel like it didn't flex or move at all. The third possible situation is where the determinant, the gamma squared minus 4mk, is negative. If you have this negative gamma plus or minus the square root of that stuff over the 2m, and you wind up with a negative there, we're going to get a complex root. Okay. In this case, our two roots, R1 and R2, are going to look like the negative gamma over 2m plus or minus I times the square root of gamma squared minus 4mk, over the 2m. This comes from using the quadratic formula as we did in the previous two cases. Recall, with a complex root, the root is going to have two parts to it, a real part and an imaginary part. The real part is going to be the negative gamma over 2m. That'll be our alpha. The imaginary part is going to be the square root of gamma squared minus 4mk over 2m. That'll be our value for beta. All right. Recall that alpha is equal to this negative gamma over 2m. This is going to be negative. Negative because as we discussed earlier, okay, we're going to have a negative sign times a positive value over a positive value. The displacement equation in this case, when we have complex roots, is going to look like what we have right here, where we have C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. Notice in this case we have cosine and sine. When we graph this, we're going to see oscillations. Okay. Notice as well, as t goes to infinity, and we're applying it to our displacement constant, once again, we're going to get e to a large negative value. So e for both terms is going to be going to 0. So over time, once again, the displacement function is going to 0 and the damper works. In this situation, we're going to have r squared is less than 4mk, which gives us, again, not r squared, gamma squared is less than 4mk, which is going to give us gamma is less than 2 square root, or in this case, we're going to have our damping coefficient is less than the critical. Okay, so we don't have critical damping in this case. This is called underdamping. In this case, what you're going to have happening is the tire is going to bounce up and down several times. That's dangerous. Okay. Let's take a look at a couple of specific examples to see how this actually works. All right, in our first example here, let's consider a system where you have a 16-pound weight attached to a spring. When you attach the weight to the spring, it pulls the spring down or elongates the spring 8/9 of a foot. It'll cause the numbers to work out. In this case, we also have a damping system that exerts a force of 12 pounds when the velocity is 2 feet per second. If we use our initial position as 6 inches upward, be careful, upward's going to mean negative, and u prime of 0 equals 1. That's a velocity of 1 foot per second. Notice the velocity is positive. That means the velocity is moving downward. So what's happened is the mass is 6 inches above the natural position, but moving downward with a velocity of 1 foot per second. In this case, you're asked to compute the displacement equation for any time t. We're going to need to, as we've done in earlier cases in the first video, first convert our weight to mass. Recall that the mass is equal to the weight divided by gravity. The weight is 16 pounds. The gravitational constant is 32 feet per second, which I'm going to skip the units for right now, is going to be 1/2. To compute the coefficient on the spring, right there, we're going to take the mass times gravity divided by the elongation. So we're going to have our mass, which is 1/2, our gravitational constant, which is 32, and then we also have our deflection or elongation of 8/9. Work those out, you get k equals 18. Okay, the damping coefficient is going to be the negative of gamma times u prime. Now, something here to realize. Anytime we're actually computing the damping coefficient, the sign on the u prime and the negative at the front are going to wind up canceling each time. For example, if the velocity is upward, okay, the force is going to be down. So if the velocity is upward, negative, okay, and the force is going to be down, positive, so we're going to wind up with this being negative, and the negative here times the negative there is going to give us a positive. The force is positive. The second thing that can happen is if the velocity is downward, if this is positive, if the velocity is downward, the force is going to be exerted in an upward direction to negate or to offset that that velocity downward, which means that if it's exerted in an upward direction, our force from our damper is going to be upward, which is going to be negative. And once again, you have a negative equals a negative, multiply both sides by the negative, and you wind up with positive. The whole point of this is, regardless which way the velocity is moving, or the mass is moving, the force and the velocity will be opposite signs, and things are going to wind up canceling out along the way, just as we discussed, and your damping force is always going to wind up being positive. Okay, so in this problem, we were told that you have a damping force of 12 pounds. There it is. We have a velocity of 2 feet per second downward. And if we substitute these into our equation, we can wind up with 2 times gamma equals 12, or gamma is 6. This then allows us to have the following values for our coefficients. The mass is 1/2, gamma, the damping coefficient is 6, and the spring coefficient is 18. This gives us our initial value problem right here. 1/2 u double prime plus 6u prime plus 18u equals 0. Here are our initial conditions. Now be careful. Remember, this initial position is 6 inches upward, which means it's in a negative direction. And we're told that the velocity is downward. So that's in a positive direction. So watch your signs on your values. To determine the type of damping that we have in this system, what we want to do is we want to check the gamma squared minus the 4mk. Let's go back up here. Here we go. At the top of the screen, once again, we can see that our gamma is 6. So we have 6 squared. 4 times m, m is a half. Actually, you can see them all over here. And the spring coefficient is 18. This is going to give us 36. Minus 36 is 0. This is critically damped. This system is critically damped. It's going to yield a double root. We can see this if we take our equation, multiply through by 2. This is going to give us u double prime plus 12u prime plus 36 equals 0. And I think you can see that that factors out pretty readily to give us a, this is going to give us r plus 6 times r plus 6 when we convert it to the characteristic equation and factor it. Okay, this gives us then the value of r as being -6. So I'm going to substitute the -6 into both terms. And because it's a double root, we introduce a factor of t into the second term. This gives us c1 e to the -6rt plus c2 t e to the -6rt. We're then going to apply our initial position. U of 0 equals a -1/2. Now the nice thing here is every place there's a t, we have a 0. Okay, won't always be the case. Okay, it can be something other than 0, but just to make life easy, we're going to assume it's, or we're going to define them as being 0. This gives us then that C1 is a -1/2, which moves us further to a complete displacement equation. We now have a -1/2 e to the -6t plus C2t e to the -6t. To compute a value for C2, we're now going to use the second piece of information we have from our initial value. And that is that the derivative of the displacement equation has a value of 1 at time 0. What this means is we need to take and compute the derivative of this equation. From the first term, we have a -1/2 times a -6, which will give us a +3 e to the -6t. Then we're going to have the derivative of our second term. That's a product rule, which is going to give us C2 e to the -6t plus C2t. -6 comes out front, which will give us a negative there. Okay, and we wind up with something like that. Substituting in 0 for the t value, this second, or the third term actually, goes to 0. And what we have is 3 plus C2 is equal to 1, which gives us C2 is going to be a value of -2. Substituting these values in for our displacement equation, we wind up with the -1/2 as the coefficient on the first term, -2 is the coefficient on the second term, and there's our displacement equation. If we graph this, the graph looks something like this. Notice the displacement isn't a whole lot, okay? But notice there's no oscillation. Okay, oscillation would look like this. But what winds up happening here, actually the oscillation with some type of damping would eventually do something like that. Okay, there's no oscillation here. What this means is that this damping system takes the initial shock and restores the mass to its original position without it springing back and forth. Let's take a look at a second example. All right, let's take a look at this next case. Suppose that you're on a team that's designing a piece of machinery, and essentially what's happening is the piece of machinery is suspended from a spring. It weighs, the the machinery itself weighs 24 pounds, stretches the spring down 8 inches, and due to the vibrations, the operation of the machinery, you wind up with an initial velocity of 2 feet per second. And notice this velocity is in a downward direction. The question is, how much damping force needs to be incorporated into the system to achieve critical damping? You don't want this piece of equipment bouncing up and down on a spring all day long. You want it to take the initial hit and then be restored to its position. Okay, so what we want to do here is we want to compute a value for gamma in this case, which means that we're not going to have to do quite as much as in the previous example. What we're going to do is we're going to convert our weight, the 24 pounds, to a mass. So we're going to have our 24 pounds divided by the 32 feet per second squared. And the mass is going to be 3/4. And once again, I'm going to assume that you know the duty units, but I'm going to skip that for right now. We'll focus on the numbers. The spring constant is going to be mg divided by L. Now be careful. Notice here for L, the elongation, it's 2/3. Well, wait a minute. Up here it says it pulls the thing down 8 inches. True, but we need to convert this from inches to feet. And if you'll recall, 8 inches out of 12 inches gives us 2/3 of a foot. So that's where the 2/3 comes from. That's a real easy thing to overlook. And boy, does it mess up your numbers. Okay. Computing this, we get K as 36. We want systems to be critically damped. If they're critically damped, that means we want to have a situation where gamma squared is equal to 4mk. We know the mass is 3/4. We know the K is 36. We've got the 4 times that, which is going to give us 108. And to get gamma, we take the square root of that. That's our damping coefficient. Okay. Well, that's all well and good, but having a damping coefficient is something different from knowing how much force we need to have being applied in the damping system. Well, this brings us then to the equation for the force of the damping system. Oh, there it is. Recall that this is going to be equal to gamma times u prime, where u prime is the velocity. We've got our value for gamma now. It's the square root of 108. Well, let's run this over to where I actually put it. It's the square root of 108 times, recall our initial velocity is 2. Multiply those together, and we wind up with a damping force of 20.785 pounds is required to achieve critical damping in this mechanical system that we're looking at. Just computing the damping force is not a horrible thing if you have a little bit of information like the initial velocity. Let's take a look at another situation. Let's consider a system where you have a 48-pound weight that elongates a spring 18 inches. The object is pulled downward with an initial velocity of 3 feet per second. Now, before we get going on much of anything, it's really wise to first list what are the values that you're given initially. First, our elongation, right there, 18 inches is 1.5 feet. You take 18 divided by 12 and presto changeo, you've got that. Initial velocity is 3 feet downward. Pay attention to downward. That means the velocity is positive. That gives us a positive 3. Notice that the object is pulled downward 6 inches. There's our initial displacement. And once again, it is converted from inches to feet. So u of 0 is 1/2. Because it's downward, it's a positive 1/2. The initial velocity is 3. It's positive, moving downward. And the elongation is 1.5. With that, we now are able to compute m, the mass. The mass is going to be the weight, the 48 pounds, divided by the constant of gravity, which is 32. Your mass is 1.5. K, which is the mass times gravity over L, is going to be the 1.5 for the mass, the 32 for the gravity, and then we're going to divide by the elongation. 1.5 feet gives us 32. Next thing we're going to do is we're going to take a look at computing our damping force. We are given that we have a damping force of 4 pounds, which allows us to plug this in here, is equal to gamma u prime. Now, we know what u prime is. U prime is 3, which makes it really nice for computing gamma, which is our damping coefficient. We have 4 is equal to gamma times 3, or gamma is equal to 4/3. Now that we have m, gamma, and k all computed, we can substitute these into our second order linear homogeneous equation. M is the 1.5, gamma is the 4/3, k is the 32, okay? K being right up here at the top of the screen. All right, so this gives us now a homogeneous equation that we can convert to a characteristic equation. 1.5 r squared plus 4/3 r plus 32 equals 0. When we substitute these values into the quadratic equation, okay, we're going to have the negative 4/3 plus or minus the square root of a negative 4/3. I'm sorry, a 4/3. Still thinking about the negative from up front. We're going to have our 4/3 squared minus 4 times 1.5 times 32. And this is all over 2 times the mass, which is going to be the 1.5. And I think you can see here upon inspection, before we even do any computations, that's going to be much bigger than 4/3 squared is. We're going to wind up in this case with a complex solution. And when you figure that out, you wind up with your two roots being negative 0.444 plus 4.579i, and then the negative 0.444 minus 4.597i. With the complex roots, we can go right to a solution, a general solution. We're going to have our e to the negative 0.444t times c1 cosine 4.597t plus c2 sine 4.597t or 597t. At this point, we want to substitute in our values for our initial displacement. The initial displacement is the 1/2. You may say, wait a minute, 1/2, where'd that come from? That's from way up here at the top. There it is. Our initial displacement was 6 inches downward. So it's positive 6 inches, that's half a foot. Okay, so this is going to give us 1/2 is equal to e to the negative 0.444 times 0. That's just a fancy way of saying 1 times c1 times the cosine of 0 plus c2 times the sine of 0. These zeros in the argument come from the fact that t itself is 0, which zeroes out both of the arguments. Cosine of 0 is 1, sine of 0 is 0, which makes this really straightforward because we now have the equation 1/2 is equal to 1 times c1, where c1 is a 1/2. We can now take that value for c1 and substitute it into our displacement equation, and it gives us this. Now comes the fun part. We need to compute the derivative. It's going to be a product rule. Okay, so when we work on the product rule here, we're going to take the derivative of this, which is going to give us a negative 0.444 e to the negative 0.444t times everything in the brackets, which is the second term. Plus, then we're going to have the first factor the e to the negative 0.444t times, now we need to do the derivative of this second factor. Well, it's going to be the derivative of this 1/2 cosine. When you take the derivative of cosine, it's going to give us a negative sine, that's 4.597t. Take that times a half and you get 2.299 sine. There really is a point in there. It's not 2,299. Plus, then we're going to take the derivative of sine. Well, that's going to be the cosine, and it's going to be the cosine of this 4.597t times the 4.597 times C2. Substituting in the initial velocity of 3, I'm going to have 3 is equal to, and now I'm going to put zeros every place there is a t. Be careful. This is going to become a 1, but its times is negative 0.444. When we substitute in 0 into what we have inside of this bracketing right here, what we're really going to do is we're going to put 1/2 times the cosine of 0. 1/2 times the cosine of 0 is a half. Then we're going to have the C2, but it's times the sine of 0, which is just 0. So it gives us this first term right there. Doing the same thing for the second term. Now we just have e raised to the 0. Well, that's going to give us 1. We're going to substitute in. Remember, sine of 0 is going to be 0. So this whole first term is gone. And we're going to have C2 times the 4.579 times the cosine of 0 is 1. Whew, made it through all of that. Go ahead and do all the multiplying and all that good stuff. And notice we're going to have a negative 0.44 times a half. Add it to the left-hand side, gives us a positive 3.222 equals 4.597 C2, or alas, we get C2 right there is 0.701. At this point, we actually have a displacement equation. When we graph this displacement equation, look what we get this time. Do you see that we now get quite a bit of oscillation? In this situation, we have what is referred to as an underdamped system. And you can see the displacement, the up and down, where the amplitude, starting out fairly large, decreases, and continues to decrease until the amplitude reaches 0 at some point, and the system stops moving. Okay. If you want, you can go ahead and compute the r squared or the gamma squared minus mk using the 4/3 for gamma, the 1.5 for m, and the 32 for k. And you'll see that this works out to be negative, which truly does mean the system is underdamped, hence all the oscillation you're seeing in the system. Okay, so that gives you a couple of problems to take a look at here. Hopefully these are helpful for you, and I hope you have good success.